Welcome back. In this lecture, we'll be talking about inverse functions. Before we get to that, let's just have a brief recap of what I mean by one-to-one functions, because when we talk about defining inverse functions, we'll be defining them specifically for functions that are one-to-one. So reminder that a one-to-one function is something like, for example, the function x cubed, which passes the horizontal line test. Any horizontal line passes through the graph of this function in at most one place. And what that means for us is that for any y value that I'm interested in, there will be exactly one x value that maps to that y value. Compare that with something that's not one-to-one, like y equals x squared. Y equals x squared is not one-to-one because a horizontal line will cut through its graph in more than one place. And so that means that for any particular y value that we're interested in, there might be more than one x value that maps to that y value. So we want to be talking specifically about one-to-one functions because what we would like is to have every one x value map to exactly one y value and to have only one x value which maps to that y value. And the reason that's something that we want is because then we can reverse the process. If you're thinking about the graph of x cubed, I can ask you the question, for the value of y being 8, what is the value of x that takes us there? And there's only one answer to that question, which is if x is 2, that will give us a y value of 8. But if I ask you a similar question about x squared, there's not only one answer. If I say, could you please tell me the x values that give you a y value of 4, there's two answers, positive 2 or negative 2. And we don't want that to be the case. We want it to be that for every input, in this case, we're thinking about the y value now as being our input, we want there to be only one output. When I ask the question, what is the value that gives me a y value of 4, I'd like there to only be one answer. And unfortunately, if there's a function that's not one-to-one, then there isn't only one answer. And that's because what I plan to do is to take our function f, which is a one-to-one function, and reverse things. So for a function f, whatever x and y points it has, the inverse function, which we write f with a little -1 as a superscript, would give us those points in reverse order. So for example, if you have a function where the x value of 2 gives you a y value of 8, then the inverse function should do the reverse. If you give it a value of 8 as an input, it should give you a value of 2 as an output. And actually, if we're thinking about the cubing function, is the one that I'm thinking about here, that's one where x value of 2 gives you a y value of 8. The inverse function, the one where if you give it an input value of 8, you get an output value of 2, that's our cube rooting function. One thing to mention about notation here, that when we write the little -1 as a superscript, that's not an exponent. So when I write something like f to the power, f with a little -1 of x, that is not f to the power of -1. That is not the same thing as f of x to the power of -1. It's not the reciprocal of f of x. When we write f with a little -1, that's meaning the inverse of f, the function that reverses the inputs and outputs from our function f of x. That's something that we're going to see a little bit later on, so just foreshadowing for the future when we get into trigonometry and we're interested in functions like the sine function, sine of x, we'll be also defining the inverse of that function, and we'll write it in the same way that we write inverses here, with a little -1. And the same thing will be true there as is true here, that this is not an exponent. We're not referring to the reciprocal of sine, we would be referring to the inverse of sine. Now, if you did want to talk about the reciprocal of f of x, if you did want to say, well, I want to have something that's 1 over f of x, then I would write that as f of x with the whole thing to the power of -1. Then that's clear that that does mean here is the function to the power of -1. That would be the reciprocal of f of x. That would be 1 over f of x. So the one thing that I want us to keep in mind as we're making our way through this lecture, well, two things rather. One of them is that when we're talking about inverse functions, we're only talking about functions that are one-to-one. And what these inverse functions do, they reverse the inputs and outputs. So if you did have a one-to-one function, and if you knew that, for example, for that function f, that if you give it an input of 2, then you get an output of 3, well, then for the inverse function, it would do the reverse. An input value of 3 would give you an output value of 2. Also to mention here is that if f is a one-to-one function, f inverse is also going to be a one-to-one function. And also, f inverse itself is also a function. So when we're thinking about inverse functions, you can say that the inverse of f is f inverse. And f inverse, if you wanted to go in reverse, you would get back to f again, that the inverse of f inverse is your original function f. Now we have a couple of properties here. These are properties of inverse functions. And this is true for any function with an inverse. So when you have a one-to-one function, it will have an inverse, f inverse, and it should have these two function composition properties, that if you compose f inverse with f, you just get your x value back again. If you compose f with f inverse, you get your original input value back again. And the reason for that, if we're thinking back to the example that I have from the previous slide, if you're thinking about, for example, these two little things that we're saying here, if you're imagining that f takes the input value of 2 and gives you an output value of 3, and if you're thinking f inverse does the reverse, then if you compose f with f inverse, take an input value of 2, let's say, put it into f, and then take that value and put it into f inverse, you get back to where you started. And if you were to start off by taking the value of 3 and putting it into f inverse, then take what you get and put it into f, you get, again, back to where you started. That's the whole idea of an inverse function, is that f inverse undoes what f does. So if you take a function f and compose it with its inverse, then you'll be taking that input value, giving you the output value of f, put that inside of f inverse, and it takes you back to the start all over again. So when we're checking to see if two functions are inverses of each other, or this is a nice way to confirm, if you have a function f of x and you think you found f inverse, how to confirm that they are inverses? Check to see, is f inverse composed with f? Is that equal to x? Is f composed with f inverse? Is that equal to x? And so let's do that now. Let's start off with checking f inverse composed with f of x. So in other words, that's putting f of x, which is x cubed plus 2, inside of f inverse. And so what I'll be doing is, in f inverse, I'll be replacing that x with x cubed plus 2. So I'll have cube root of x cubed plus 2 minus 2. And then just simplifying from there on in, the plus 2 and the minus 2 cancel each other out. And then x cubed, cube rooted, that would just be x. So if you take f inverse and compose it with f, it just gives you whatever that input value of x is back again. And let's do the same thing for f composed with f inverse. So that would be putting cube root of x minus 2 inside of f. And that means for f of x, we're going to be replacing that x with that cube root of x minus 2. So instead of x cubed plus 2, it'll be the cube root of x minus 2 that gets cubed plus 2. The cubing and the cube rooting undo each other, and the plus 2 and minus 2 cancel each other out, leaving us with just x. One thing just to say about these two functions, and this is again why it should be not a big surprise that these functions are inverses. If you're thinking about what f does for every input you give it, f first starts out with cubing whatever your input is, and then it adds 2. So with f, we start off with cubing, and then we end up with adding 2. If you're looking at what f inverse does, f inverse starts off with whatever input you give it. It begins by subtracting 2, and then once it's done the subtracting 2, then it does the cube rooting. Now, one thing to notice here is that f and f inverse, they're doing opposite actions in the reverse order. First, f of x cubes things. The last thing f inverse does is cube root things, and those are opposites of each other. We also have that f as its last move adds 2, and f inverse as its first move subtracts 2. And adding 2 and subtracting 2, again, are opposites of each other. This is the reason why, if you're looking through the work that we did earlier on, why all the operations canceled each other out quite as nicely as they did. Why the plus 2 and the minus 2 canceled each other out, and then the cubing and cube rooting canceled each other out. Or for the other one, the cubing and cube rooting canceling each other out, then the subtracting 2 and adding 2 canceling each other out. This is not a big surprise. We'll see this with some other examples that we do in a little bit, where you'll see that f and f inverse are basically doing the same thing, but opposites and in the reverse order. So similar activities. Here it's cubing and adding 2. Here it's cube rooting and subtracting 2. These are opposite activities, and they're being done in reverse order, opposite order of each other. But we'll see more of that in the future. So for the graph of an inverse function, this actually comes back to that first example that I gave, that I said if you knew that f of 2 was 3, then that would mean that f inverse of 3 would have to be 2. In other words, f inverse has the same points, but with the coordinates switched, with their orders switched. So if you're thinking as far as points go, that means that if you had 2, 3 is a point on f, then 3, 2 is a point on the graph of f inverse. Or more generally, if you have any point a, b on the graph of f, and if you do have an inverse, then BA would be a point on f inverse. So if you're thinking about taking the graph of f and using that to find the graph of f inverse, essentially all you'll be doing is taking all of your points and switching the order of first coordinate and second coordinate. In other words, we're switching all the y values and all the x values. That also means that you'll be switching any y properties and x properties. So, for example, for f, you can find whatever its domain and whatever its range is. And for f inverse, remember, domain, those are x values. The domain of f, that would be the range of f inverse. The range for f, those are the y values. Those would be the x values for f inverse. The range for f would be the domain for f inverse. So again, everything is being switched. Whatever was an x thing for f will now be a y thing for f inverse. Whatever is an x property for f will be now a y property for f inverse. So that also means things like asymptotes switch. If f has a vertical asymptote x equals some number, then that means f inverse will have a horizontal asymptote of y equals whatever that number is. If f had a horizontal asymptote of the line y equals some number, then that means f inverse will have a vertical asymptote of the form x equals whatever that number is. So everything will be switched. X and y points, switching their order to give me the points on f inverse. Anything that's a horizontal asymptote for f becomes a vertical asymptote for f inverse, and reverse is also true. And they switch their domains and ranges. Now there's one other little thing that I mentioned here, that this business of switching x and y values is really the same thing as reflecting your graph in the line y equals x. So one thing that you will see is that if you're graphing a function and its inverse, that's the same thing as taking whatever you have for your graph of f and reflecting it in that dashed line. So if you have something that's in quadrant 2, well then it would be reflected to now be in quadrant 1. That would be something where you could think about the inverse as being a kind of reflection or a kind of symmetry. This is different than, of course, being even or odd. That's a separate thing. But you will see this in the next example when I graph a function and its inverse, that they are reflections of each other and reflected in that line y equals x. So I'm going to graph here those two functions that we started with, graphing f of x, and then I'll also graph f inverse. Just before I get to this, I know what these are. This is the cubing graph, and it's been shifted upwards by 2 units. This is the cube rooting graph, and it's been shifted to the right by 2 units. So I'm going to graph both of these. I'm going to take my cubing function, and I'm going to now shift it upwards by 2 units. There we go, and I'm going to just label my points there. So I have the point 1, 3, and I've got the point 0, 2, and I've got the point negative 1, 1, and there's my graph of y equals x cubed plus 2. Good, good. And I'll do the same thing with the cube rooting function. So I'll start off with my cube rooting function. And I'll move that to the right by 2. Good, good. And now I'll label my points. So I have the point 3, 1. I have the point 2, 0. And I've got the point 1, negative 1. And there's my graph of y equals cube root of x minus 2. So a couple of things just to notice here. We've already confirmed that these two functions are inverses of each other. We confirmed that a couple of pages back. And one thing to notice here is that, as I expected, the points on f and the points on f inverse just have their coordinates switched. F has the point 1, 3. F inverse has the point 3, 1. F has the point negative 1, 1. F inverse has the point 1, negative 1. We have the point 0, 2. We have the point 2, 0. That we have exactly the same points, just with their coordinates switched. Also, if I were to draw on this graph the line y equals x, we could see that f inverse is reflected across that line and gives you the graph of f. That one function is just the reflection of the other. That if you're thinking about that x cubed plus 2, reflecting it on that line y equals x, that would be the graph of x cubed minus 2. So we'll do another little one here. So I've got a graph. Again, 3 points have been given to me. I have 4/3, negative 1. I have 2, 0, and I have 4, 1. First off, it's asking me to sketch the graph of f inverse, and before I even think about that, we should just confirm that f inverse exists. Remember that if you're a function, as long as you're one-to-one, then yes, f inverse will exist. And if we're looking at this function that I've graphed here, every horizontal line I draw passes through that function in at most one place. So this is something that is a one-to-one function, so definitely f inverse will exist. And so here we go. I'll just mention a few facts. One would be, if we know that these are the points on f, then f inverse will contain the points -1/4, it'll contain the point 0, 2, and it'll contain the point 1, 4. The same points, just with the coordinates switched. The order of 1 4/3 going in the order -1/4, 2, 0, switching it to be 0, 2, 4, 1, switching it to be 1, 4. We know that this graph of f of x has a vertical asymptote x equals 1, so that means f inverse should have a horizontal asymptote y equals 1. Furthermore, if we're thinking in terms of domains and ranges, if we're thinking about this function f, for f, its domain is just all the values that are bigger than 1. There's nothing at 1 or to the left of 1. So in other words, my domain is everything from 1 to the right, not including the 1. And that the range, if we're looking at all the y values go all the way down to the bottom and all the way up to the top. We'll have that the y values are any real number. So that means that if I'm thinking about f inverse, that whatever the range was for f, those are the y values, those will be the x values for f inverse. Whatever the domain was for f, that's the x values, that would be the range for f inverse. So f inverse should have a domain of all real numbers, and it should have a range of 1 to infinity, of just numbers that are larger than 1. So I've got all the information that I need now. I have my 3 points. I know that it's going to have a horizontal asymptote, and I know what I'm expecting for its domain. So now let's plot that away. So I'll start off by drawing in my horizontal asymptote. So there's y equals 1. We had the point -1/4. We had the point 0, 2. So if we're going back and just confirming, we had again the points -1/4, the point 0, 2, and the point 1, 4. And just to draw what I've got, and if we're looking at this, taking a look at this graph and comparing it with the graph that I have on the previous slide, you can see that yes, the one that you have on the previous slide, if you were to imagine reflecting it in the line y equals x, you would get the shape that I've just drawn on the other slide. You would exactly have the shape that we've drawn. So I will say that yes, we've got a nice graph here of f inverse, that if this is what f looks like, then f inverse should look like this. Also notice that the domain and range are exactly as I predicted. I said over here that whatever the domain was for f, that should be the range for f inverse. F inverse should have a range 1 to infinity. That whatever the range of f was, that should be the domain of f inverse. The domain should be all real numbers. And if we take a look, we do exactly have that. The domain is all real numbers. The graph continues in all directions from left to right. But for y values, it's only y values that are larger than 1. There's nothing on the graph at 1 or below it. So as predicted, we do indeed have the graph of f inverse. I'm just going to label this as f inverse of x. I don't actually have an expression for what is f of x or f inverse. All I just said was here is the function f of x, here's its graph. So I don't actually have anything algebraic to write for it, but I'll still label that as f inverse.